Okay, so my name is Andrzej, as also introduced me, and I am going to teach this and the next course alone, and maybe help a little bit Jenkins with the introduction to Python. The idea here is that we will have a, let's call it a crash course on linear algebra. And this is really a crash course in the sense that by no means I am going to cover the topics you have in a regular, let's say, mathematics curriculum where you have linear algebra for 1 or 2 semesters. And here I'm going to give you a 2 hours lecture, basically. So I will introduce some concepts and notions from linear algebra. I will try to make, the idea was to make it as consistent as possible, so that we reach a point where you will understand, you will have all the basic knowledge to understand the backpropagation algorithm for learning neural networks. So the thing is that when we talk about the neural network, artificial neural networks, or we talk, of course, about deep learning, but this really doesn't matter. This is just deep, means just that we have more layers. The problem becomes more complicated in terms of computational power and resources that we need to perform the computations, but the idea is always the same. And of course, as you heard, what you know maybe about neural networks, we have to learn them first in order for them to be useful. Now, the learning process, it is based on some evidence, on some data, that we have some examples and that we want the neural network to train to. And there comes the problem that, okay, so basically neural network will contain a lot of parameters, numerical parameters, and we need to set up the values for these parameters. So the thing is, how do we do this setup? How do we make sure that the next time with the next iteration, our network is learning, so that it performs better and better? And the mathematical foundation for this is something which maybe you have heard about, is the optimization problem. And we are basically trying to find a minimum of a complex, complicated, maybe I don't use the word complex here because it has a different meaning in mathematics, but a complicated, very complicated function, okay? But the idea is that we want to find an optimum of that function. And since this function has, it's not usually you have seen in mathematics, okay, we can have a function, and then you have these so-called local and global minima, and of course the maxima. The maxima we are actually not interested in, but this is a dual problem. It's just we can take minus this function, and maximum problems will become minimum problems. So the idea is that we'll be looking for these minimum forms. Now, this function is maybe still not that complex in terms, complicated in the sense that it has, if you draw the axis, it has a function of one variable, and you have the value, which is the y, which is the response, let's say, variable. Now, in neural networks, basically we have the same problem. We'll have a function, and we want to optimize, so we want to find the minimum of this function. The problem is that if you would recall the picture that Ross was showing you, the convolutional neural network, the number of these variables, like x's, is counted in millions. So you don't have one dimension, you have millions of dimensions. And this function becomes a multi-dimensional function, multi-valued function. And in mathematics, this is a well-studied problem. There are many algorithms for optimization. It's all a branch of mathematics. There is a lot of literature. But what we are going to look at is to look at methods which are gradient-based. So the main kind of mathematical concept that we'll need in order to understand how the neural network is being learned is, in terms of the mathematical foundation, is the gradient-based optimization. And the crucial word here is the gradient. So all my two lectures that we are going to have is basically to give you an explanation for what is a gradient. So maybe I could ask you a question: who knows what is a gradient, or have heard about a gradient, or knows how to calculate, whatever, any idea what is a gradient of a function? 1, 2, 3. Okay. So in this sense, I think this course will be good. I mean, it will be good for you to go through this. And I have prepared this course, as I said, a linear algebra crash course. I'm not covering by no means all aspects of linear algebra. I've just selected the topics or the concepts, the notions that directly will lead us to the gradient. Okay, so what I'm going to show, it is prepared in like a mathematical course, so the same way you would. I would try to have it as in a math class. While you see, I'm not using the PowerPoint or slides. I'm using the Blackboard, the traditional way. But this is in fact the only way to learn mathematics. And we will go rigorously through all the theorems. I will give you proofs. I will show you how to prove things. But I will not cover all the stuff. So we are really encouraged, and this is not only for this course, but also for your later, the courses that you will have in semester 2, semester 3. If you have time, please really, I mean, learning mathematics is never lost of time. So try to get some linear algebra books. Try to learn a little bit more, read whatever you find interesting. Maybe it will be a starting point for you to study a little bit on your own if you don't feel comfortable with these things. And the books in mathematics, they will be written. This will be done in the way I'm going to present. It's just that I'm not going to cover everything that usually you have in a linear algebra, let's say, course. To start. One thing, for example, I'm not covering, which is a crucial thing in linear algebra, is the notion of the determinant. I kind of assume that, okay, we will not use it, we don't need it, determinant, but you probably had this already in high school. So you know that you solve equations, you build some kind of an array, and for that array you have two equations. Okay, so this is, let's say, like this. And then we were trying to solve, okay, these were given, and we were trying to solve for x, and then you were building something which was called computing the determinant, so then you were putting these things and with different combinations and doing something like this, right? So then you were calculating this times this minus this times this. So this was in high school. This is in linear algebra. This is a general thing. There's a whole theory. And this is very classical, basic, first year mathematics. But as we don't directly need it here, I will not cover this. But you are really encouraged to look into this if you want to see how to solve, let's say, systems of linear equations. This is the basic thing. So you can read on your own a little bit. Okay, so you can come and ask me questions if you want more advice, how to start reading that, how to learn more. But we are not going to cover this, although this is a very, very basic classical thing you start with. I'm just going directly into the things that are necessary to understand this. Okay? But what I'm going to show you is going to be rigorous and kind of also serve for you how to study mathematics. Okay? If you need later in the course, because this is an interdisciplinary program, you might come across notions or concepts that are kind of advanced, and to understand them, it's okay, I need to know some mathematics, go back to my textbooks, And then, of course, mathematics is a little bit different than other subjects. It's a way of learning it, a way of kind of getting to know the notions, the concepts, understanding things. So I will try to present it here. Okay. So we start with very basic notions, and the first part. Okay. So I will put it maybe the same way I have in my lecture notes. The lecture notes will be available. I will put them on Moodle. So I will just write it. As I said, try to do it as a math course. So I'm going to write down things because you need time to kind of digest the knowledge that is presented here. And please also ask questions if there is something unclear or I write badly and you don't see, cannot read my handwriting. Also, please let me know. So vectors and matrices. Okay. So these are two one mathematical object which has two types, and we start with a definition of these. Okay. This is the first things we need: matrix. So matrices is the plural of the word matrix. And we say that a matrix of dimensions, so a matrix of dimension, and we will write this as n times n over a set of real numbers. Okay, so this is the way we denote the set of real numbers. Okay, so real numbers, everybody knows, right? So basically any number you can think about that you see in your is usually real. Okay, but this is a particular case. In general, we will talk that we have a matrix over a field. And I will introduce what is a field in a moment. Okay, so I will give you a definition. But for the moment, we say real numbers because this is something you know. But in general, matrices are defined for over any field F, and we will see what it is. We will define it shortly. And basically, a matrix is a function. So this is a function. We denote this matrix, let's say, as A, which operates on so it has, as a first argument, it takes a set of m elements, 1 to up to m. The second set is from 1 up to n. So, right. And returns, so you can, okay, maybe I should, yeah, that's okay. I can write like this, and it returns a value in R. Okay. So, here I am using the notation, so I'm kind of defining the domain of the function and a codomain. Okay, so maybe you, just a remark, this is the way of writing function. So usually we had this rule that okay, we had a set x. So the function was defined for a function f was defined on elements from set x, and the values were in y. Right. So this is the same thing. It's just that now we have two sets here. We have a Cartesian product of two sets. One has m elements, one has n elements. And if we know the values of these two arguments, then we know the value of the function. Okay, it is a real number. And usually we will denote this, so we will say that we have a, like we used to have at school, let's say that f, the value of function f at argument x was y, here we will have that, okay, we have now two elements, so we will use a pair, ordered pair, ij, where I is from 1 to m, j is from 1 to n, and this is something which is in the set R. Okay? And we can even say more. So we will say that this is equal to a j, which is a real number. Okay? And the thing is that, okay, you will never see a matrix written in this form. This is a formal mathematical definition. Usually what we do, we write matrices as arrays. So what you will commonly see is this. If you have a matrix which is A, and you see that this is element A11, this is element N2, and so on. Then we have element 1n. Then, you see? Yeah, it's good. Then we have the second row, which is A to 1, A to 2, and so on till N to N. And we continue down, and then we have the last element in this column, which is AM1, AM2, and finally we have AMN. So a matrix of dimension m times n. So usually we denote it as an array which has m rows. So these are the rows, 1, 2, up to n. And then we have n columns, column 1, column 2, column 4. Okay? And so all these numbers are arranged in this two-dimensional array. And then, of course, if we want the value of the function or the matrix A at a particular point, we give kind of the coordinates of which column and which. So this is basically the which row, which column. Once we specify the numbers, then we know what is the value in this setup. Okay, so for example, for column 1 and the row 2, so this is column 1, this is row 2, we have A to 1. Okay? So then, once we have a matrix, we can also define a vector. So we will have another definition, which is definition 2, maybe this is 1. We will define a vector. And a vector is a special type of a matrix, basically a matrix which has dimension n times n. So we say that a vector of dimension n is in fact a matrix, or we can, maybe I can write it in method form. We say that basically matrices of dimension n times 1, so the number of columns is basically 1, are referred to as vectors. Of dimension n. And usually when we write a vector, we then write it as a column, and then we put the elements of a vector. But now we know that there is only one column, so we don't use the second index. We just write the elements, and then we have elements. Okay? Clear so far? No? So this is just two basic notions. What is a matrix? What is a vector? Okay. So how do we write? And now there are a number of operations that we can apply to vectors or to matrices. Okay, so we will be like we have numbers. We can add numbers. We can multiply numbers. We can subtract numbers. It's kind of a similar thing with matrices. We have a set of operations that we can perform on matrices. Okay, and these operations that we will consider here are, for the moment, we take 3 of them. So this will be the addition of matrices. We will consider the multiplication by a number. So we have a number and a matrix, and we multiply. And then we have transposition. And the fourth operation will be the multiplication of matrices. So this is a little bit more complicated, but who has seen? Well, I guess all you are kind of familiar. But just as a repetition, we quickly go through all this. Okay, so let's first look at the matrix addition. So we say that the sum, so we take the matrix A plus B, of 2 matrices of dimension m times n. We can say is calculated entry-wise. We'll just in a second explain what it means. So what happens is that if we want to take AB, so this is the summed matrix, right? So this with this we denote the sum of these 2 matrices at element. This is a shortcut for writing that we want the value of this function at arguments ij. This is simply the entry. That's why we also say entry-wise, because we take the entry at ij in matrix A, and this is a real number. So then we know how to do the addition, because this is a real number. This is a real number, okay? So this is well defined. So then this is normal, regular summation plus, like we add 2 numbers. And then we put this number in the right entry of this resulting matrix, which is A plus B. Okay, is this clear? So we can take an example, but maybe first I will point out here, this is a crucial point. So this operation of addition is defined only for matrices which have the same dimension. So we cannot add matrices, let's say 2 times 3. One matrix, let's say A is 2 times 3, and matrix B is 5 times 7. No, for that we don't know how to do the addition. Okay, they have to be, so there are 2 matrices. Of 2 matrices, and maybe also add here A and B of dimension m times n. So there are 2 matrices, but the dimension is 1. It's only m times n. It's well defined. So how do we do this in an example? So, okay, I will take maybe another example here, not the one in the lecture notes. So let's say that my first matrix A will have elements. So this will be a 2 times 2 matrix. Okay, maybe let's not make it square, let's make it more interesting. Okay, so this is my matrix A. plus, and then what I know I want to make the addition, I have to have a matrix of the same dimension, so again 2 rows and 3 columns. Then I fill it with some numbers. And then I do the addition. So what this tells me is, okay, do it entry-wise. Entry, so these are the entries, the numbers basically are called the entries in the matrix. So what I do, I basically take the corresponding entries and I do the addition. So I take, let's say, first we will take the element 1, 1. So this is 1 plus 0. And this is put in here. A little bit more space here. Then we take second, so they have to match, so this is 2 plus 7, which we put in the second part, and then we have 3 plus 1, which is similarly we do for the row below, so this is minus 5 plus minus 5 pieces. Then we have 7 plus 3. And then we have 9 plus minus 2. Okay, and then we can, so now we know how to do this addition because these are numbers, as said before. So this is simply 1, here we have 9, here we have 4. This will be minus 10, this will be 10, and 9 minus 2, which is 7. Okay, so this is how we perform matrix addition. Okay. So then we take the next operation, which is the multiplication by a scalar. So
you can use them for multiple. No.
Yeah, yeah, can
No.
multiply. Yeah. So see, okay, we call it matrix, not scalar. Okay, so we're going to multiply a matrix by a scalar. So then, so we say that the product A, okay, so C will be our scalar, A will be the matrix. And here's an explanation so of a number. And this is also known as a scalar. Scalar is basically a number in this context. C and a matrix A is calculated multiplying each entry by C. Okay. So then it means that if we have Ij, so this is the multiplication, so it's a matrix which we look at element in the ith row and the jth column. It's simply C times Aj. Okay, so this is the normal standard multiplication of two numbers. Okay, and as an example, let's see another matrix. Let's say these are different. So what we get as a result is this, that we have to multiply each of the entries by number. So this will be 3 times 1, 3 times 0, 3 times 2, and as a result we get 3, 0, 6, 15, 21, minus 15. Okay? So this is one thing. And then we have a operation that is maybe, because this is like similar to addition and to multiplication of numbers. I mean, okay, we have a matrix, but somehow there is nothing special here. I mean, we just multiply. Finally, we just multiply and add numbers. So different in this respect. Operation is the transposition. And here basically we say that a transpose of an n times n matrix A, okay, is the, so now what we do, we reverse the dimensions. So this will be n times n matrix. We noted A with a T as a subscript. And this one is obtained by turning rows into columns and vice versa. So this has a very concise mathematical notation, because the ith element, the element in the ith row and the jth column of the transpose matrix is simply the element which is in the jth row and the I column of the original matrix, right? So if we take an example, for example, 0, 2, so let's say, okay, so this is let's say the original matrix A. So then A transpose. So what we say here, you change the rows into columns and columns into rows, right? So then this is a column, we make it into a row. This is a column, we make it into a row. Then we have a column here, we make it into a row. Okay, so that's basically flipping these elements either by columns or by rows. So we could take this row and make it into a column, this row, we could basically make it into a column. Okay? So this is just like rotation, or, well, actually not really. Because if you would rotate, then 7 would come first. But here it's the 3 which comes first. So it's really like take the row and you put it down this way. Okay, so these are the basic operations, most basic, fundamental operations that we have on matrices. Of course, we can apply the same to vectors. So it's just that vector is a matrix which has one dimension 1. So for example, and this is often used, a vector, if we have a vector V, which has, well, I'll say 1, 2, 3, we can transpose the vector. So then we transpose is simply the column made into a row, so then it will be denoted. Okay. Right. So now let's. Is this clear? Any questions? Or it's yeah.
Does that, what you mentioned in the beginning, that the dimensions have to be the same between the two matrices, does that hold for all the operations?
So it holds for, for transposition it doesn't matter, because transposition takes only one matrix, so whatever dimension, like for example a vector or a matrix, that's okay. For addition they have to be of the same, dimension. For multiplication by scalar also doesn't matter, because we have only one matrix. So there is no correspondence in here. But we will have a correspondence in this operation that I'm going to present now. Not correspondence, but we'll have a restriction on the dimension. So now we will look at the multiplication of two matrices. So we have two matrices and we want to multiply them. Okay. So this is a little bit more, maybe if you see it for the first time, this might be a little bit more complicated, but yeah, that's it. So the difference is that here we were saying about scalar multiplication. Now we are going to change it to matrix multiplication. So not a scalar, but matrix. And here, so let's start with A, which is an so if A is n times n matrix, and B, now the thing comes, so if B is an m times n, so A is n times m, and B then has to be, this can be anything. These have to match. The number of columns have to match the number of rows. Okay. The other dimension is anything. So we could take P. So n, and this is important that here they match. And we will see in a moment why. So let's write these matrices in the form as before. So we have A1, 1, A1, 2, A1. So number of columns is n. Then we have A1, A2, 2, and 2n. And we continue here. And finally, we have n rows. So then this is n times n. Then we will write B in a similar fashion. But now we will have the B elements here. So 1, 1, B, 1, 2, B, 1. Number of columns is P, so we have P here. Into 1, B, and 1, B, 2, and then B, P. Okay, so then these are our matrices. And what is important here? M and M here. Okay. The first dimension, the number of rows is n. The number of columns is n, and the number of rows is n. Okay. So then, if we do the multiplication, so then we have then the matrix product. which will be known as, let's say, C. This is C is equal to A. You could write a dot here, but usually people don't write anything. It's just A and B consecutively. Is then N times P matrix. So we have a change of dimensions here. Now these outer dimensions, they will appear here and will disappear. Okay? You will not see M in the final result. Maybe I can write it. Okay, which one's this one here? So C, of course, we will write it again as C11, C21, up to C. And now we have n dimensions, or n rows, and p columns. C1p, C2p, C and P. Okay. And now the question is, what are these lines? Okay. So now it is not that straightforward anymore, and therefore, where for I equal 1 to n, j 1 to p, c I j. So the entry in this, each entry in this matrix is in fact as this form. So we write ij, so we have to take the first row, I row, and the j column. We'll just write and explain how this is obtained. So then we have the number of columns, which is n, times e, the same here, n, j. Here. Can you see this? Okay, so now in order to calculate the element, the entry in this matrix, we have to do m multiplications and sum them. Okay, so we do ai1 times b1j plus ai2 times b2j and so on up to ain times bmj. So this looks maybe not that nice. I mean, it's the formal definition. It's exact, but maybe you don't really see what is going on when you look at this formula. But I will shortly explain how this can be done in a kind of so that you can memorize how to do these calculations. So the idea is that we will have a drawing in the lecture notes, but I will just explain here on the blackboard. It's easier just by showing you these two matrices, and then in the lecture notes we'll have this picture. But the idea is the following. So when you want to compute the entry, let's say C21, which is in this in the second row and the first column, then you have to look. So we follow this formula. But basically, what you do, you take the row and respective row and respective column from these two matrices, and you kind of you put the column on the row, and you kind of do the multiplication and summation. Okay, so let's say we have the C21. Okay, so then it means that we should look. Our I is 2, our j is 1, and this is equal to, and then we rewrite this formula for this particular entry. So everywhere where we have I, we put 2. And wherever we have j, we put 1. And then we will see what is happening. b2 1 plus a2, this is n, times b n 1. Okay. So if you look at the b's, you will see that you always have the first column. Okay, this is the column 1, column 1, column 1 with these. Now, if you look at the A's, you will see that you multiply row 2. You only look at row 2. So this is the row 2, maybe this I can mark with, so the first index here is 2. So, in fact, what I do, I take row number 2 here. I can maybe take it with a different color. Yellows, maybe it's more visible. So I take this row, okay, from my first matrix, and I take my first column from the second matrix, and I put the row kind of on top of this. That's why the dimensions have to match, so that the length of the row is the same as the height of the column. Okay, so I overlay them, and then I do the multiplication element 1. So a to 1 times b11, a to 2 times b21, a to m times bm1, and do the summation. That's how I obtain this particular entry. Okay. So this is basic. This is the basic matrix. So let's maybe have an example. Practice on how does it look. Or maybe I can keep this so you can see how this works, and then we take. So let's say that A is. I will come up with hopefully some small numbers here. So now my matrix A has dimension 2 times 3, and I have a matrix B. So then B has the columns have to be 3. So then I have to, the rows have to be 3. So I have 2, 1, so then I have to have, okay, 1. I don't want to put big numbers here. Let's try this. Okay. And now what I want to compute is the multiplication. Okay. So then we can see that this is a matrix of dimension 2 times 3. This is 3 times 2. So what will be my output matrix? So what will be the size? 2 by 2, right? So then I have a 2 by 2 matrix. Okay, maybe I write the parentheses later, because I don't know how big this will become. So let's see. So as I said, you have to take the corresponding, so you have basically 2 times 2 entries here. So you have to, for each entry, let's take the first entry, I need to multiply the first row by the first column, okay? And do the addition. So this is 2 times 1 plus 3 times minus 1 plus 1 times 0. Now, so this will be the first element, okay? So this is this one times this one. Now I do the second, so I take the second row times this one. So this will be 1 times 1 plus 0 times minus 1 plus 2 times 0. So then this is the row, which is 2 times the first column. Okay? And then we have the remaining one. So then again, this one, the second row times the first column. So then I will have 1 times 1 plus.
So the first line, the first row,
Uh,
and the first,
So you said first.
first
The
row.
second. Sorry. Yeah.
Yeah.
Second. Yeah. Exactly. So you have 2 times 2. Well, yeah. So this is confusing. I mean, the reason. Plus, and then you have 1 times 3. 1 times 3. And then finally we have the last. So this is 1 times 2 plus 0 times 1 plus 2 times 3. So then we can compute the final outcome, which is 2 minus 3 is minus 1 plus 0. So this is minus 1. This is 1, 0, 0. So this is 1. You have 4 plus 3, 7 plus 3, 10. And then we have 2 plus 0 plus 6. So we have hopefully I will. And you see that, okay, we get a small matrix, but actually we have to do a number of calculations, right? So this matrix multiplication actually is quite expensive in terms of computational time. There are more complicated operations like matrix inverse. I'm not talking about this now, but you can also look up these things, how to compute an inverse of a matrix, but not for all matrices you will be able to do this. But yes, this is the basic operations that we have for matrices. Okay, and you can I'll give you some examples on this for homework. Let's say for exercise or put on modeling. I can make this out to practice this thing. This is very basic. So in all machine learning, you will always have this multiplication, and later on when people just do this in a symbolic way, they will only use letters basically and perform all these operations like equations with matrices, where actually they just write A times B transpose and so on, well, addition and stuff. So, but behind this you always have these operations. So it's good that you see at least once. Okay, so this was more like algebra, what I was showing you. Okay, so like addition, multiplication, like you have in school. It's just that this is now with different types of objects. Okay, and now we will look into something which is maybe more abstract, and we will introduce some notions from abstract algebra, because we need to give a construction of something which is called a vector space. Okay, and so one thing that in mathematics people often use the same names for things that are quite different. So I was introducing you a vector now, which was like a function, which was assigning values values to indices basically. So you have indices of the entries, and then you have values. Now I will talk about vectors in a more abstract way, and then we will see how these two types of vectors actually match. Okay, but forget now about what we discussed so far for a moment. So we will not look at these operations for some time. So this was just to kind of refresh or learn you how when you have matrix operations, vectors operations. And now we will go to something which is called vector spaces. And we can be more general, talk about different vector spaces. Okay. So this is one of these basic notions of abstract algebra, and it's how people call it an abstract algebraic structure. So in mathematics we talk about different objects in general, and we have different types of objects, and we have to kind of construct them. Okay, so we will use, like you have Lego where you build more and more complicated structures from simple pieces. This will be done in exactly the same way. So we will define some basic structures and then use these structures to define more complicated structures. And in our case, the goal is to define a vector space. Okay? But in order to start with this, I need to introduce two smaller or less complicated objects that we will use to define the vector space. Okay? So just to mention that we will talk about abstract algebraic structures. These structures, in general, if looking in a general way, they consist of two types of elements. One are the sets. So we have a finite number of sets, and we will have a finite number of operations on elements from these sets, which lead to some elements which are also in these sets. Okay, this is very generic description. For the moment, for some of you, maybe it doesn't really make much sense what I'm saying. But you will see in a moment when you see three definitions, and you will see how they are kind of, what is the common thing for these definitions, okay? So, the construction is the following. I will start with something which is called a group. Then the group will be used to define something which we already mentioned, the word field. And once we have the field, we will be able to define the vector space. So these are these abstract algebraic structures, with one more complicated than the other, and we will see them one by one. Okay? So I will start with the definition of a group. So, we say that a group which is a pair, and I will denote it like this, is a non-empty set G. Okay, so some set, think about this as general as possible. I mean, you have no basically no intuition in the moment, but these are just some set with some elements. Okay.
Is that G comma 0?
Comma, it's not 0. It's you can see it as a dot. I just want to use a circle, open circle, not to confuse you with standard multiplication. It is in fact called multiplication. Multiplication is one of the examples, but it is more general. So I write it as a small open circle. Okay. So we have the G, and this is what you asked for. So together with and we call it operation, and this operation is exactly the circle which operates on the product. Cartesian product of G and returns an element. So this operation takes element from G, another element from G, somehow combines them and returns us an element from G. Okay. You can think it of as a function. It's like a function from G to it's defined for every combination. So it's, in fact, this operation is a function. But usually we use the name function for numbers. In group theory, that's why it's called abstract algebra structure, because these elements can be anything. You could think of a group of fruits, apple, banana, whatever, and some operations. So let's say you take an apple and a banana, and it returns you, I don't know what, strawberry. So this is very, very generic, okay? And but there are some limitations, and I'm going to write them down. There are some limitations on what kind of criteria this operation needs to satisfy. So we have this operation that we write it formally for any two elements from G assigns a uniquely define element in G. And that satisfies the following conditions. Also referred to as axioms, mostly axioms. So we have our operation, and the conditions are the following. So one is associativity. Which says that if we have for any three elements from G, then it holds let's try to write this more clearly. Space here. So you see it clearly. Okay, so basically it means that it doesn't matter in which order I do the operations. I can do first G1 times G2. So I said times. It's not. It doesn't have to be multiplication, right? Because it doesn't have to be numbers. But I can apply this operation to the first two elements. So I will get an element from G, and then I apply, so this is in G, and then I have another element in G, so all in all I will get an element in G. And what this says is that if I do it in this order, or I do first G2 combined with G3 via this operation, and then have this applied with G1, I will get the same element.
Doesn't mean that it can be like multiplied, divided, subtracted.
So the thing is that here we have no. That's the thing. So we have no. I mean, it could be. You could think about this as multiplication. You could come up with a group where your operation would be multiplication, and this could be. And you have, let's say. I mean, if we take real numbers, okay, or natural numbers, and addition, this is a group, right? Because I can take n1, a natural number plus a natural number plus a natural number satisfies this condition, right? So I have a group which is G is natural numbers, this circle is a normal plus, and you can check that this condition is satisfied. So any two elements, 2 plus 3 plus 4, it doesn't matter that I add first 2 plus 3 and then 4. I can add 2, 3 plus 4 first, and then 2, right? So this is
So this operation you're defining here is like a more generalized form of
exactly.
operation.
It could be any operation, just that it satisfies this first the conditions. This is the first condition.
Okay. This is a representative of all possible operations, or is this one type of operation?
Any operation which satisfies the conditions. Okay. So the second condition is existence of the identity element. So it means that there exists an element, okay, let's call it B in G, So this says that there is an element in our set such that if we apply our operation to this element and any other element which is in the set, in any order, the order doesn't matter, we obtain this, the second element, okay, whatever it is. So, for example, if we go back to our natural number examples, do you have an idea what is E? And we have natural numbers with addition.
With addition to 0?
0. Right. So if we take 0, 0 plus anything is anything, right? The original number in any order. So then we have the.
Can I ask, why then if E is 0, 1, why we write E and not 0?
Because this can be general.
Oh, okay.
This can be anything.
Okay.
Okay, so it could be that I could take another group which is, let me see if now I'm not, because I'm just taking it out of my head, but you could have addition modulo n.
Okay.
So your circle could be plus mod, let's say 7. I think this would be a group.
Okay.
So then you have your G, which is
G.
0, 1, 2, 6. This is a finite number of elements. And then your circle is this summation modulo 7. And then you can check that your operation will satisfy these. Hopefully. But yeah, I'm going to check. I'm just taking it out of my head now. So this is a group, right?
It's a group.
Yeah.
So this exists, I'm just trying to understand it in real terms. For example, if we consider natural number, so 1 is a natural number, 2 is also a natural number.
Yeah.
So 1 into 2 is 2 into 1, that's what you're saying.
No, so I'm saying that so this is how you read. There is an element in G, at least one.
Yeah.
But one such that when I take this element and we combine it with my operation with G, in any order, the order doesn't matter, I get the other element as a result. So it doesn't take me somewhere else, it will give me as a result my element that I was providing it with E. Okay, so I have two elements, E and G. And if I give G and combine it with this natural element, I will get the G. So that there is such an element, it can be more than one, doesn't say, but it has at least one. So there exists, you know,
Like an element that does not have any effect.
exactly, something like that. Yeah, you have
No, I just want, because initially we wrote in the second line of the definition that any two elements in G assigns a uniquely defined element in G.
yes.
So isn't this like a corollary to that? From that?
No, because this is a special, there's exists an element, right? So I could say that if I could imagine that I would have an operation that would take me out of the set G. So for example, if I have, I don't have an example at the moment, but I could come up with something that, okay, my set G is, we could have it here, that if this is G, but I would change this to 8, this would not be a group, because then if I take, let's say, 2 plus 6, I would take 1 plus 6, it's 7. Modulo 8, it is 7. And 7 is not in G. So then the definition would not hold. So this would not be, this set with this would not be a group, because 1 plus 6, which are two elements from G, combined with this operation, addition modulo 8, it is 1 plus 6 is 7, modulo 8 is 7, but 7 is not in the set G. So I have to add 7 to my set to make it a group.
Sorry, can you give an example which holds, like,
Which holds this one. Because 1 plus 6 is 7, modulo 7 is 0. So I get an element which is in my set G.
But in that case, 6 plus 2 is also 8.
No, 6 plus 2 is 8, but modulo 7
So if we were looking at the last example, 6 plus
with
2,
8.
6
With
plus
that.
2 was 8. So why is that not holding?
6 plus 2 is 8, modulo 8 is 0. So this would be okay, but I can find a pair, 1 plus 6, which is not okay. So it has to be for all possible combinations, any G, any elements I choose from G, any two elements I choose from G, they have to give me, the operation on these two elements has to give me an element in G. So yeah, that's a good point. So of course, 2 plus 6 would be fine, because this is 8, modulo 8 is 0. But 1 plus 6 is not fine, so then this is not a group.
Okay, but in the example 7 that you were trying to say, then that also not holds, right? Because not all elements give you 7.
No element will give me 7.
I mean, you get 7 only by 6 and 1. You don't get 7 other than that.
3 and 4.
1 and
I
2
think
is not
one-
7.
1 and 2 will not give you 7. So it does not hold.
Yeah.
No, but it gives me 3, right?
Yeah.
1 plus 2 is 3, modulo 7 is
Ah,
3.
it's
And
for
3
the
is
group.
in G,
Ah,
because it's
okay.
always modulo 7.
Okay.
So this is, the result has to be in the set.
Okay.
That's the, yeah, but it's a good question because then it clarifies
Yeah.
the concept. And it also teaches you how to read these definitions. Right? Okay, I'll just check. I think maybe it's slow. We have still, Ross, do you know we have still 5, right?
We still have 15 minutes.
15 minutes. Okay,
Yes.
good.
We also need to highlight homework.
Yeah,
So it's,
I will give you some. Okay, so let me just finish the definition of the group, and we will finish with this probably here. So there is existence of the inverse element. So now we have that for each G. So any G that I take from my set, there exists G minus 1, we denote the G minus 1, which is the G, so another element such that G times G minus 1 is, maybe I should write it, well, unfortunately, but yeah, okay, I write it here. G times circle minus 1 So what it says is that if I have any element, I can find another element in G such that if I put them, combine them or perform the operation on these two elements in any order, I will get my natural element. Okay? And then you can check for this example that basically this is the case, right? So usually with groups, what you do, you can let's make it more, maybe this example more modulo 5, okay? A little bit easy, like shorter, or maybe more instructive. You don't have that much to. We can play with this example a bit. So what happens now is that you have, we do the addition modulo 5, okay? So then we add all the numbers, so if we have 1 plus, I should have one more, maybe like this.
No, 0, 0, 0, 2, no.
0,
0.
1. Pluralities. So we have 0 plus 0 is 0, and then 0, 1, 2, 3, 4, right? Now we add 1, so if we have 1 plus 0, 1, 2, 3, 4, and now we get a 5, modulo 5, we get a 0. 2 plus 0, this is 2, 3, 4, this is 5, so this will be 0, and this will be 1. 4 plus 2 is 6, modulo 5, it is 1. And then we have 3, 4, now we will have 5, so we have 0, so we have 1, 2, and then 4, 0, 1, 2. So then you see the full table, because here we have a finite set, we can write the full table. And of course 0 you see is a natural element, because 0 plus anything gives us the anything, right? And the same in the other order. So the order is either this way or this way. So this is 0 plus 0, 0 plus 1. So 0 comes first, but this one is, when we look at the column, 0 comes second. Okay? So you see that this holds. You can check this condition easily yourself, maybe. So we just check this one. Okay, we have the 0 element which satisfies this condition. And now we want to check the last property, so that we have the inverse element. Okay. So what if we look? So we have to have it for every element in our set. So we look at 0. 0 is easy because 0 with itself is 0. So it has its own inverse element. If we look at 1, we want to see where is the number that we get to 0. So we look in the row and we find, okay, this is 4. And now we have to check that the other holds, but this is easy because this is like 1 plus 4 modulo 5 is 0, or 4 plus 1 is 0. So we have this. And then we do the same for 2. 2 plus 3, 3 plus 2, we get 2 zeros, so it's okay. And for 4, we already checked with 1, right? So for 1 is 0, 1, 4 is 0. So we checked all the properties so that we know, okay, we have a group, because this operation with this set satisfies the condition. Okay. So let's maybe some minutes so we can. Are there any questions? Still.
What's the application of the group?
The group will be used to build a field. The field will be used to build a vector space. So this will be like an element of a construction that we reach at the vector spaces, and all the vector spaces we will do. We will have some operations that will be used to later on with the columns.
So you're basically deriving the entirety of linear algebra with its little graphic elements, its little axioms. It's like a most general proof of linear algebra.
Yeah. So this is like the general construction of the structures that are used to introduce the vector space. Because with the vector space, then I will be less general, because then I will talk about. I mean, I will give you the general definition, but then when we go for calculus, I will just focus on one example that will be most important from your perspective, because then it will be just a course in math, which is not really the purpose here. So this is just to give you just the basic foundations to construct what we need, and then we can use that for computing the gradient, which will be the optimization problem solution. So used as a solution to the optimization problem in neural networks. But also the point with this is that it's like a little bit training on math, so that you have this kind of mathematical, because this is the first course in the master for space informatics, and there will be more advanced courses, and then you can see, people will assume, okay, you know the math, right? And this is like, we also take this opportunity to give you at least a chance to, if there is something missing, you know how to how to learn math, how to read these mathematical rules, how to do the abstract reasoning. So these are very basic things, but hopefully it might be that later on you will need some background, and then you are on your own. You need to read math books to get the to kind of learn the concepts, and then you can see this kind of description in the math books. And then how do you read this? How do you imagine this? So it's a little bit of training to get you familiar with how to, because you are also from very different backgrounds, and this is also a way to make sure that, okay, to some extent you have the same capabilities for the coming courses. So that's a little bit of a training for the future, basically. It's also like a way to give you some foundations. Of course, this is not complete because there's no time to be complete, but at least some basic things so that you can think in a mathematical way and that you can have a chance to then learn on your own if needed. Because this is a very interdisciplinary master program, and people from different backgrounds will, like engineers, computer scientists, very different people will have courses with you. So hopefully this will help you later on.
I plan on studying this, of course, but do you think exams and assignments in the future will have formal proof, like rigid proof and stuff?
No, I don't really think. It's more, we're also not going to, like, this is a project-based assessment, so we are not even going to have anything of like these exercises as exams, let's say. No, this is not the purpose here. So this is more for you to take it as a way to, as an opportunity to see this abstract way of thinking, because it might be useful for you later when you need to learn something yourself. Okay, so that's why we'll just use these two courses to get you a little bit familiar with these things. Because we don't really know what, I mean, you are from a very diverse background, so that's okay. So maybe if we do some exercises for homework, if you want to. So I didn't this time cover much of these. There are some things and maybe not that much exercises. There are some abstract exercises, but maybe it's not very useful here at the moment. This is maybe more for you to, I will put the lecture notes online so you can read it and go through this once again. But maybe just to make you more familiar, because this actually will, this first part, this algebra and matrices, this will be used quite frequently later on. So maybe we could have a few exercises where we could say, let's say, I could write it in this. I will also put it on Moodle. And then the exercise is that you write what is the V transpose, okay, so the vector, and what is the transpose of the vector. We could have exercise 2 where you have a matrix A. Maybe we can put them. Okay, and then the question is what is. Addition. We could have a third one where we have, okay, let's maybe do also some operations here. So what is, so I will use the same matrix. So what is A transpose? A second question could be what is 5 times A? This would be like a scalar. Let's maybe do also here you could consider this thing. So you take A transpose plus B transpose and sum them. And to check, maybe you could also have a look at the difference. What happens if you do that? Okay. And and maybe one example on multiplication. So you could have what should I have here? I need one more matrix. So let's say C. And okay, and then let's make it more complicated. And then the question is, what is A times C? Okay, so I'm using this one in this example. Okay. So I'll also make a photo of this one.
You could ask them what is the zero in the group of matrices and their addition?
Oh yeah, that's another.
Is it a good,
That's a good, yeah.
is it a related part?
So we can also have a, yeah, so,
Is it a little puzzle? But don't tell us.
so the fifth, so we will consider a group, okay, G, and we will use the, I didn't define, but let's do the same thing we had. So we had modulo 5. But G will be the set of, let's say, matrices of size 2 times 2. So we have this definition of matrices. So we consider that we have all matrices that are of size. Okay, I should. Oh, this G is not more.
It's a square.
Because no, this is a square matrix, but I want the elements have to be up to 4, 0, 1, 2. So this is not really. Okay, I have to. How should I write it? Okay, so G are matrices. I will write it. Are matrices. Let's say of dimension 2 times 2. So that's square matrices, 4 elements, where. And let's make this, I call it A, where A, I, J is in the set, and it will be clear. Okay, so the values that you can have, the entries of the matrix are just numbers from 0 to 4, where this 4, so this will be a more like a, or we can write it in a more compact way. So these are the indexes, which are 1 or 2. And the question is, what is the neutral element? In G. And the addition, because I didn't define it, so I should also tell you how to do the addition. So if we have A plus B AJ, this is equal to basically do the same addition as we did it. Okay, so A, B, of course, or just to make everything clear, where A, B are the elements of G. So that is one, right? So you know what is the operation, you know what is the G, what is the set, and then what the question is, what is the natural element. Okay?
I don't understand. What is the neutral? How do you define neutral element?
Okay, I already traced it, but you have it in the this is the second point in the definition of the group.
So the question is asking you to define it.
Yeah.
In the example there we had this group 0 to 4, right?
Yes.
And then for each element we
So there
had
is
another element that combined would be the neutral element, which
I
is
don't know.
we wanted 0.
Yes.
Yeah.
No, I think it's IG.
The
IG?
inverse.
Yes.
It was called the third point in the definition.
Oh, that was the inverse.
The
Okay.
inverse element.
Okay.
Yeah.
We just wanted to that would.
If you want, you could also consider what is the inverse element. Let's say, but then I have to give you the matrix. Like for this question,
Yeah.
you have a matrix, which is, let's say, 2, 0, 1. Let's put 0. Let's put 2, 3, and 2, 1. That's it. Okay. And you could think what is the inverse element in this group.
That would give the neutral. Okay.
So you have to know what is the neutral first, and then say what is the inverse element to this one.
Okay.
So this could be like additional question. Once you have answered this one, what is the inverse?
Maybe it helps to think what is the neutral element this way.
Okay,
Yeah.
that's perfectly fine. So this is together with this. So this is, let's say, 1. Question 1. This is question 2. It's a little bit like a bonus question.
your definition is that group and passes it from 4 to 5 numbers.
So the elements, like the values with the entries, are numbers from this cell.
And I and
These are the indices, so this is the way to say, okay, this is the informal way to write that you have to the elements. You always use by so this basically means that this how to write maybe once you it's like an element. Usually not big A, right? So this is like an entry in the matrix. So